I guess I'm finally ready to start. Now that it works. The topic is radicals. They are easy. You will find that the material this week far easier than the previous week. Let us start with, as usual, some definitions. What's this symbol mean? The square root. The square root of a number being equal to this other thing is only true whenever you can take that other thing, square it, and get back to A. Now there's a caveat here though. I'll put an asterisk here. Both A and B have to be non-negative, is what it says. Both A and B are non-negative, and if that happens, then you have this biconditional statement, where if I had this writing, then I could follow the arrow the other, back this way and achieve this statement. Or conversely, if I had this, then I would get this statement out of it. And this caveat down here with the asterisks is super important. For example, the square root of 9 is equal to 3 because 3 squared is 9. When you were in grade school, like I guess maybe elementary or middle school, they would have told you some nonsense about the square root of 9 is equal to plus or minus 3. That's not really true. The square root of 9 cannot be minus 3 because minus 3 is not non-negative. That's the primary reason, is it does not fit the definition. It is true that minus 3 squared is 9. Yeah, that's true. Just like it's true that if I started off with the statement x squared equals 9 and rearranged it to say x squared minus 9 is 0, and then factor this, I can factor it because x squared minus 9 is what? It is a difference of two squares. So it factors like x minus 3, x plus 3. And you can see there's two roots to this. But this is not, let's throw this across the room. This polynomial is not the act of taking the square root of 9. Square roots are non-negative. It has an official name, the one that, when you take the square root of 9 and get 3, it's the principal root. We are only interested in the principal root. It is a very sophisticated discussion to want to talk about the other roots. If I write this, it means that there is a 2 here. This is called the index. And the only time no one writes the 2, the only time no one writes the number is when that number is 2. Because we will investigate when it has a different index, an index different from 2. If that index changes to be something different from 2, our definition still works. The nth root of A is B, provided that B to the n power is A. And we still have a caveat, but that caveat will only apply if n is even. So that means you can take so that means if we were looking at the third root of some number, that number could be negative. And if it is, then the result will also be negative. For example, the third root of 8 would have to be 2, because 2 cubed is 8. The third root of minus 8 would be what? Minus 2. And why is that? We will make use of this fact. It is a rephrasing of the square root in terms of an exponent. The exponent is 1 over n. And then you can use your exponent rules to do all your manipulations. We will also use this fact. It says the root of the products is the product of the roots. I think that's everything. Let me do an quick example of these two things. The square root of 81 is 81 to the 1/2 power. I know that 81 is 9 squared. And then if it's to the 1/2 power, I'd have the 1/2 out here. And when you have this sort of arrangement of exponents, what do you do with them? Multiply. And what's 2 times 1/2? So this is 9 to the 1 power. And you can see that, sure enough, this is working just fine, because the square root of 81 must be 9, since 9 squared is 81. other fact said that if I had the product of two radicals, it was the radical of the products. So evidently this is the square root of 2 times 2. Which just says that it's the square root of 4, and I know the square root of 4 is 2. Then evidently, taking the radical of, I got these two radicals, they're identical, I multiply them together and I lose the radical. Right? An alternate way to see that would be that it says 2 to the 1/2 times 2 to the 1/2. And what do I do with exponents when they're in this configuration? You add them. This is x to the m times x to the n equals x to the m plus n. You add them. So this would be 2 to the 1/2 plus 1/2, which adds up to, so it's 2 to the 1, which of course is 2. We can simplify things that are not perfect squares. What is this divisible by?
3.
This is divisible by 3. How come?
8 plus 1.
Which is divisible by 3. Therefore, 108 must be divisible by 3. So I can write this, I can write that 108 as 3 times some number. It's 3 times 36. Right? And then I can say, well, that's square root of 3 times the square root of 36. Now, do we know the square root of 36?
Yes.
Yes, it is 6. So our answer here would be 6 square root of 3. It's customary to write the integer in front of the radical. You want to avoid saying square root of 3 times 6, because we don't want people to think that we just stopped our radical short, and that really we meant to bring it all the way out here and it was the square root of 36. So to avoid that problem, we say 6 square root of 3. One of these days I'm gonna figure out how to make this, optimize this real estate up here. But minus the square root of 81. Is that a real number? Yes. What is the answer? Negative 9. Because what is it saying? It's saying to take this negative 1 and then way over here figure out the square root of 81. Square root of 81 is 9, so it must be negative 1 times 9. Is this going to work out? Yes, the index is odd. So it is okay to have a negative under the radical. Tell me two numbers that 729 is divisible by. A little quicker. 3 and? Nope. It's only divisible by 6 if it's even, and divisible by 3. But that rule about being divisible by 3 also works for 9. For 9. If it's divisible by 9, if the sum of the digits are divisible by 9, then so is the number. If the sum of the digits are divisible by 3, then so is the number. So this number, 729, is divisible by both 3 and 9. Do what? So what I will write is, this is the third root of minus 9 times 81. Maybe I'll employ some of that notation with the exponent. So it's really to the 1/3 power. And 81 is 9 squared. So I'm going to have 3 9s inside these parentheses. It was okay for me to just tack that minus symbol on there. I don't need to say that because they're the same. In other words, minus 1 is identical to minus 1 cubed. And what do we get? Negative 9. Because what do you do with these exponents? Multiply. Is this divisible by 3? No. It's not divisible by 9 either. But it's even. So it's divisible by 2. So you can start peeling off 2's. This would be 2 times 2048 peel off another 2 from the 2048 and get that this is 2 squared times 1024. And I can peel off another 2. And you just let me know whenever you recognize the thing that we're peeling the 2's off of. 2 cubed times 512. Is 512 familiar to you? It is. How? Okay, do it again. 2 to the 4th times 256. Do we know 256? It's 32 what, squared? Okay. What is the significance of these numbers? Yeah, but there's something even more pronounced. Take out your cell phone. How much memory does it have? Probably says it on the back. My note I think has 512 gig. 512. These are all powers of 2. Computers use binary. Binary is where the only numbers are 1 and 0, or 0 and 1, however you want to put it. These are the only digits. Let me rephrase that. Instead of having the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, in binary you only have the digits 0 and 1. You can still make all the numbers. It just looks different. And because there are just 2 numbers for the computer to work with, then all of your storage capacity is going to come in a power of 2. Uh, 64 is just 8 times 8, right? Sixty-four is 8 times 8. 8 itself is 2 cubed, right? This is 8, and then it's times 8. So 8 times 8 is 2 to the 3 plus 3, which is 2 to the 6. And very conveniently here, this are to the 1/6 power. So our final answer is 4. It's 4 because you would have 2 to the 6th to the 1/6 times 2 to the 6th to the 1/6. That's 2 times 2. Alternately, we could have just said that 4 to the 6th, yeah, that's 4,096. If for whatever reason we knew that, then we could have just jumped straight to the answer. square root of 24. Well, 24 is not a perfect square. I need to start factoring 24 until I can recognize it where some of those factors are perfect squares. The perfect squares are the numbers like 2 squared, 3 squared, 4 squared, and so on. How about 4 times 3? That's 12, and then times 2 would be 24. Four to the 1/2 is what? 2, because it's just the square root of 2, so we would conclude by saying this is 2 square root of 6. 6 is composed of 2 prime numbers. It's built out of a 2 and a 3. There's not a pair of anything, so it won't have a perfect square as a factor. Questions? Is this easier? Is this easier, sir? In the answer? Okay.
If I have 4, 3, and 4.
If that 2 was a 4, if this was our answer somehow, then in the step before it, you would have seen this. You would have had to have had a 4 squared under the radical, because the square root of 4 squared is 4. It would have been 16. It would have been 16 times 6. So it would have been 96. This is square root of 96.
So why wouldn't it be like you did the 4 to the 1/2 and you got 2, right?
Yeah.
So if I had 4, 3, and 4, why wouldn't I have another 2?
Oh, if way back here it said 4 times 3 times 4.
Yeah.
Yeah.
So
Then you would have, then, but, but you would not have, it would not make this out here become, hold on, let me see. So, work it up here, we're having more room. This is just 16 times 3. So the square root of 16 is 4. It wouldn't be 4 square root of 6 is the deal. It would be 4 square root of 3. Because look, you're saying if what if that 2 was instead of 4? Okay, then I won't be left over with a 6. That 2 has something else to pair up with now. This 2 gets to pair up with another 2. What would the prime factorization be of 432? It'd be 2 cubed times 3. This one up here says 2 cubed times 3. This one down here says 2 to the 4th times 3. You see how there's an even number of 2's?
I see 4. Okay, yeah, I see.
There's an even number of 2's in this one. So all of those 2's will come out of the radical because they're pairs.
So you're basically pulling out all the pairs.
Pairs. Because in this case, the index is 2. I need pairs. If the index was 3, I'd need trios.
Gotcha.
Okay. This is not divisible by 3 or 9. It's not even. When I'm trying to detect how this what kind of factors this number has, check to see if it's even. That's the easiest one. Check to see if it's divisible by 3. That's the second easiest one. 9 is right on par with 3. You can do them simultaneously. Don't worry about 4. You can't look at any of the evens, in fact, because if it's not divisible by 2, in turn it won't be divisible by any other even number. So you would skip 4. The next one to check would be 5. Do we know what it takes for a number to have 5 as a factor? Yes, it must end in a 0 or 5. If it's divisible by both 2 and 3, then it's divisible by 6. Well, this one's not divisible by either 2 or 3, so it certainly won't be divisible by 6. There is a rule for 7, but it's challenging. I don't even know. I used to know what it is, but I don't anymore. And to check to see if it's divisible by 10, it has to end in the 0. So there we checked all of the numbers between 1 and 10 except for 7. And sure enough, that's the one it's divisible by. This is negative 7 times 169. Do we recognize 169? It's 13 squared. So I have a negative 13 root 7. We get it? It's okay with everyone? express the radical in simplified form. It's the third root of 80. So I don't look for pairs, I look for trios. If I factor 80, I need 3 identical factors in order to get a simplification. Well, 80 is even. In fact, it's divisible by 10. So it's divisible with 2 and 5. I can view this as the cube root of 8 times 10. But 8 is 2 cubed and 10 is 2 times 5. So really I am looking at 2 cubed times 10. I don't need to simplify the 10 into 2 times 5 because having that extra 2, having that fourth 2, isn't going to make it any simpler. I'm only going to be able to simplify it when I have a trio, when the exponent matches the index. And what's my answer? It's 2 cube root of 10. 2 cube root of 10. Make sure you understand that this 3 is fitting down inside the little hook of the radical. Do not go down to the answer choices and try and write 2 cubed square root of 10. These are different. They reasonably look like they're similar in notation, but very, very different numbers. So I will type my 2 and then use this tool right here, the nth root tool. And it gives me kind of a blank template where I can put the 3 as the index and the 10 down here. Now here right next to it I will type, or maybe here right before, come on, thing. Look at the difference. So you have to make sure you understand what you're constructing. On the second version, the 3 clearly goes with the 2. The 3 is clearly the exponent on the 2. But on this first one, I am saying this 2 times the cube root of 10. Okay? You don't have to put the dot there, but I put it there to exaggerate. All right, let's take a break. start doing it with problems like this.
You just submitted something. Yeah. But it should be good too, though. I don't think that one should be one for sure. You just submitted something, right? You didn't like the picture. No, I don't know. It is
What's the index of this thing? 2. So this is really let me write it like this. This is really 2 squared times x cubed times y to the 7 to the 1/2 power. And since the index is 2, then I need pairs. Well, now it's factored. Just because that's an x and a y instead of a 3 and a 5 or whatever doesn't make a difference. It's still a symbol, and it has an exponent. So I will get this thing written so that I have pairs of those symbols. And then the stuff that's left over is an x and a y. You can see it still has 3 x's and 7 y's, 2 2's. But then I can say this is 2 2 squared x squared y to the 6th, and then that is to the 1/2, and then the leftover stuff is to the 1/2. So, what is the number that's out in front of the leftover radical? Two xy cubed. And then the stuff that's left over is the square root of xy. Question? What's the question? Yeah. So all I did here was change the 4 to a 2 squared. Okay. And then when you consider the whole thing, I wrote it with the 1/2 power instead of the square root. All right, so we're good to there. At this stage, because the index is 2, I want pairs. Right? It's for the same reason that 2 squared to the 1/2 is 2. But if I had 2 cubed to the 1/2, while it's true that's 2 to the 3/2, I would like to write it as 2 squared to the 1/2 times 2 to the 1/2. It would be 2 root 2. Now, so I've gathered together all the pairs, and they are right here. And just like if I had x cubed times y squared times z to the 4th, and I wanted to raise that to the 2nd power, it would be x to the 3 times 2 times y to the 2 times 2, and then z to the 4 times 2. It's just an application of the exponent rules. But my exponent on the outside here is a 1/2. So I need half of all these exponents. Okay. Mm-hmm.
What if the exponent for y is like an odd number? If you divide by half?
It is an odd number to start with, right? It was a 7. My index is even. My index is 2. So I need pairs. So if it was y cubed to the 1/2, it's true that this is y to the 3/2, but that's not simplified. The goal was to simplify it. So I need pairs of y's, but it still has to be equal, so I write y squared times y. Rosalind, are you watching?
Yes.
Do you see what I've done? This answers your question of what
Yes.
happens if it's odd.
Yes. 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 It does.
Then I have y squared to the 1/2 times y to the 1/2. Do you see how this one simplifies? It must, because the 2's will cancel. Okay. What if it had said y, what if it had said y to the 10th, but it was the 3rd root? I don't want pairs anymore, I want trios. So how would I rewrite this?
It would be y
To what power?
to the power of 2.
No? Is this a 2?
No, it's a 3.
It's a 3.
Y to the power of 3.
No. If I wrote it y to the power 3, then I got to write y to the power 3 times y to the power, I got to write all this. Do you want to do that? Do you want to write this, or would you rather say y to the 9th times y? The exponent that I'm wanting trios. So y to the 9th is 3 trios of y's. Okay? And then how does this simplify?
Y to 10
Times
y.
the cube root of y. Okay? Uh-oh.
I think it would be 2.
Yeah, not 3, 2. No, wait a second. 6 divided by 2 is 3. Oh, you mean the number out front is a 2?
Yes.
Yeah, I don't know what happened. So here I don't want groups of 2. I don't want groups of 3. I want groups of 4. There's that minus symbol. 81 is 9 squared, but 9 is 3 squared. So 81 is 3 squared times 3 squared. That's 3 to the 4th. And y to the 8th is a multiple of 4. So this will simplify completely. Make sense? Both those exponents are even. All the exponents here are going to be even, and my index is 2, so this will simplify completely. Answer is 2 y to the what? Z to the we good? All right. Switching gears a little bit. They ask us to simplify this sum. Square root of 3, that's as simple as that one's going to get. But the square root of 48, what am I going to do? Okay. Is that as far as it'll go? This is your example you were looking at earlier. Because when we were looking at that problem earlier, it was the square root of 24. And that had factored like 4 times 3 times 2. And you said, what if this was a 4 instead? That would simply mean you had another 2. Isn't that 48? And this simplifies to be there's a pair of 4s, huh? Look at how it would be rewritten. It would say 4 squared times 3, and it's all to the 1/2. The square root of 3 I like. What's the number out front?
It's 4. It's 4 before.
Four squared to the 1/2 power is what? 4. 4 squared to the 1/2 power is 4. And then you have the 3 to the 1/2 power. That's just the square root of 3. And then now we have our 4 out front. So the square root of 48 is 4 square root of 3. This problem they gave us is simplified to be minus 2 root 3 plus 3 times 4 root 3. Ultimately, we get 10 root 3. Mm-hmm.
That's not part of that radical 48. You want us to add the,
It is.
it is?
Trace this out. So we have square root of 48. 48 is 3 times 16, isn't it? That's what that says. It says the square root of 3 times 16. That's square root of 16 times square root of 3, which is 4 square root of 3. So this right here is that part.
You just multiplied
Okay. 4 radical 3 is square root of 48. So then it says exactly what this says.
Yeah, that's what I was asking.
Yes.
Okay.
4 radical 3 is square root of 48. So then the problem they gave us is identical to this statement. It's a minus 2 of these root 3's plus 12 of these root 3's. So, all in one line, you could say that this was, well, that doesn't.
Quick question.
Yep.
When you got 10, did you do the 3 and the 4 with the negative 2 and then got 10?
Mm-hmm.
Okay, that's just, I'm making sure.
3 times 4 is 12.
Mhm, right, and then the negative.
So when you consider for a moment that all this says, so I want to look at minus 2x plus 12x. And then I want to take x to be equal to square root of 3. And then it's the same thing.
Okay. Thank you.
Mm-hmm. I wonder what will be the radical left over on this one. What is special about 4, 25, and 100? They are all perfect squares. Square root of 4 is 2, square root of 25 is 5, square root of 10, square root of 100 is 10. So, this will become 5 times the square root of 4 times the square root of 3 minus the square root of 25 times the square root of 3 plus 3 times the square root of 100 times the square root of 3. In turn, I would get 5 times 2 times root 3 minus 5 times root 3 plus 3 times 10 times root 3. Everybody good on this one? Here we have 3 root 3 plus 3, sure there's a lot of 3's floating around. Here I can do this, I can factor out of 3 and say that this is root 3 plus root 75 plus root 12. And root 75 was we just did it, it was 5 root 3. And then root 12, we just did it, it was 2 root 3. If I'm going to factor stuff out, I can even factor out square root of 3. I have 3 root 3 times 1 plus 5 plus 2. It's just instead of like in the previous problem, we just straight added them together, like minus 2x plus 10x. You can also apply the distributive property and just be adding integers. This would say the same thing as 3 root 3 plus 15 root 3 plus 6 root 3. We good? Any questions here?
So, that's, you multiply the 3 on the outside, you distribute the 3 on the outside. Or you just multiply it.
Right, so each of these terms has a 3. The GCF is at least 3. And so I don't like to carry around heavy bags. So I can just kind of move it to the outside by the distributive property, and they're equivalent. Then I'm only having to look at square root of 3, 5 square root of 3, and 2 square root of 3. Or really, what I'm saying is that this is 3 times root 3 plus root 75 plus root 12. And I'm just simplifying this part. It simplifies to be this. Now they all have a root 3. I can factor out the root 3 too. Or I can sit here and just add it up. This is 1 root 3 plus 5 root 3s plus 2 root 3s, which is 8 root 3s. 8 root 3s times 3 is 24 root 3. Same thing as,
You just multiply it back in.
yeah. Well, I not really. This, I have my 3 root 3, and then it's times 8. So that's 24 root 3.
It was just the way I understood it.
6 of one, half dozen another. It really doesn't make a difference. Actually, you should understand all of the ways.
No, I understood how you explained it.
Okay. Simplify, multiply, and then simplify. So I should distribute in the root 2 and see if I can get that root 10 to somehow get simpler. Trading roots. That's all it is. The root 2 is not going to go away. But I can, so what it will say is I'll have 4 root 2 plus root 2 times root 10, that's root 20. What is root 20?
4 and 5.
20 is 4 times 5, so the square root of 4 times square root of 5 is 2 root 5. There, we have multiplied by distribution and simplified. This is it. Any questions on this problem? The last two I can see immediately what the answer is. Can anyone else?
-5.
How do you do that? How'd you know?
Well, I checked the example and you kind of explained it, but
What did it say?
it just showed the way you simplify you cancel out the roots, and it's 2 minus 7, which is -5.
What do you mean by cancel out the roots?
She would love to teach us. Square root of 2 times square root of 2 is square root of 4.
I don't want to foil this out.
-7, positive 7.
No, I don't want to foil this out.
You don't.
No. I'd be wasting my time.
7 plus 2 is
Not 7 plus 2. What kind of pair is this? It is a conjugate pair. And a conjugate pair will FOIL together to give you a difference of 2 squared. The first term will be the square root of 2 squared. And the second term will be 7 squared. And you will have their difference. The first term is the square root of 2 squared. We will have their difference. And the second term will be the square root of 7 squared. And you can see the answer immediately. 2 minus 7, -5. Because it is a conjugate pair. Way back in the day, the Greeks, when they were doing math, I'm sure the Greeks still are doing math, but I'm talking when they invented a bunch of stuff thousands of years ago, they had this method for multiplying 2 large numbers. So if I want to multiply together, let me write down my conjugate pair. On the number line, this would look like there's A, and this distance is B, and this distance is B. So then this number right here is A minus B, and this number right here is A plus B. Okay, then let's multiply in the style of the Greeks. If A was 100 and B was, I don't know, 13. Then it means that the two numbers they were multiplying together would have been 87 and 113. 87 times 113 would be like a problem that they're looking at. Now I'm sure that they could have multiplied that together just straight away. So this is really advantageous for very big numbers, because they had books or sheets, they had computations of a whole bunch of perfect squares. So it was easy for them to find what a perfect square multiplied to be. And that's exactly what would happen here. Right? If I'm trying to multiply 87 times 13, I would really realize that it says 100 minus 13 times 100 plus 13. And so my answer would be 100 squared minus 13 squared. And that's how they would do it. So we need to take advantage of things like difference of two squares whenever we can. So what's the answer to this last question? Too slow. What's the answer to the last question? 9. How? How do you know? It's 20 minus 11. It's the square root of 20 squared minus the square root of 11 squared. 20 minus 11. In case there's a missing link here, when we say conjugate pair and difference of two squares, it works on anything, not just perfect squares. Even though this conjugate pair, a minus b times a plus b, is a squared minus b squared, you can directly substitute the a with a square root of a, and you can substitute the b with a square root of b. Square root of a minus square root of b times square root of a plus square root of b is just a minus b. That's all we got. That's the whole homework. It's not even 8 o'clock. There's a midterm this week. It's week 6. You'll notice that on the homework, nowhere did they have you type in the answer with exponents in radical notation. So there was not a problem like say this one. But there is a problem like that on the midterm and the signature assignment and the final. Works just the same way, 6 times 1/2, that's 3. 2/3 times 6, that's 4. And then it's over x. Okay? So you will see a problem that's something like this on the midterm. I did my best to drag this out today. I even burned off 20 minutes at the beginning, goofing around with the TV. But that's it. I told you that this week it's just simpler. So, is there anything else you want to talk about? the discussion board, what does it say? Oh, never mind. I remember.
It's about the scarecrow.
The Wizard of Oz.
Yeah. I'm glad you brought that up. Because this discussion board it used to really get on my nerves. Not so much anymore because it's happened so many times. But if we carefully read that question, the discussion prompt, it is not having you correct the scarecrow. I don't want you to say Pythagorean theorem anywhere in your post. Don't say it. Don't tell me what Pythagorean theorem is. Don't say Pythagorean. It won't help you. It will only make me think you weren't paying attention. The problem is not to discuss Pythagorean theorem. You are to analyze what the scarecrow said just as it sits. You don't want to say, here's what the scarecrow meant to say. Because I don't care. That's actually not what the problem is. The problem is for you to determine with your math if there are any triangles, isosceles triangles, that satisfy what the scarecrow said. The statement that was made is as follows. For any isosceles triangles the sum of the square roots of any two sides is equal to the square root of the remaining side. Does the discussion prompt, so I'm sure some of you have it open in front of you, does it say for you to determine the truth value of this statement? Or does it say for you to determine if there are any triangles that satisfy the statement? If we are supposed to determine if any triangles satisfy this statement, then we have to check every one of them. The statement is clearly false. So on the one hand, the statement is not the Pythagorean theorem. That we recognize. Okay, we're done with that. Number two, the statement is false, because it does not work for at least one isosceles triangle. We can identify at least one isosceles triangle where it doesn't work. Here goes my isosceles triangle, and for it to be isosceles, just simply these are the same length, and I'll pick this one to be whatever. And it ain't gonna add up to, you know, the square root of 10. Here, I'll maybe pick something easier. This will be 9 and 9. The sum of 9 and 9 does not equal square root of 5. This says the sum of the square roots, it would need to be equal to the remaining side. Even if I purposefully designed an isosceles triangle where it would get satisfied, like say, if this was 9 and 9 and 36, that's an isosceles triangle, then square root of 9 plus square root of 9 is equal to the square root of 36. That's true, isn't it? It just says 3 plus 3 is 6. However, you can't do it on any two sides because square root of 9 plus the square root of 36 is certainly not the square root of 9. So there, so far I've given two counterexamples to the statement. It does not work for any isosceles triangle because I just produced two where it didn't work. Right? But we are supposed to do something stronger than that and determine if there is any triangle, any isosceles triangle in existence where this will work. So you have to check them all. How do we do that? How can I check them all? What is the property of an, what is the main property of an isosceles triangle? That's of any triangle. What makes it isosceles? Okay. Then let's label a generic isosceles triangle that could be any of them. So for example, this is a specific one. I picked 9, 9, and 36. Those are specific numbers. Why don't we use a variable for the side lengths? That way the side lengths can be anything you choose. What should we call them?
A and B.
A, and B. And what are the two ways I can pick any two sides of this triangle? I can pick A, and then B, or I can pick A, B, and then A. Is there any other ways? If we assume that this A is equal to that A, they aren't distinguishable. It's not like this is A1 and A2, they're both just A. Are there any other ways to pick two sides? No, that's the only two ways. So then write the two mathematical statements, just like I did here. Show how there's a contradiction. What would this equal? And what is the other equation? This is a system of equations. And we want to know where what A and B have to be to satisfy this system. Focus specifically on the second equation. This equation, I claim, is a property from week 1. And you can tell me what property it is. Huh? Yes. This is the additive identity. Namely, it says that B is equal to what? 0. If I want to solve this system, if I want numbers A and B that satisfy this second equation, then B must be 0. B must be 0. If B is going to be 0, then square root of A plus square root of A is 0. What does that make A? 0. Square root of 0, which is 0. You're done. You've now shown that A is 0 and B is 0. The triangle that satisfies that statement is the degenerate triangle. It is a dot. It is a point. Its side lengths are all 0. It's isosceles. It's equilateral. It's a right triangle. Its area is 0. Its perimeter is 0. People don't usually talk about it because it ain't worth looking at. It's degenerate. It has shrunk all the way down to nothing. And if you go ahead and do that with some triangle, then that statement will get satisfied. That's how wrong it is. That not only does it not work for some, but it does not work for any bona fide triangle. And that's the solution. Very proud that y'all got the additive identity. That's great. Yes, it essentially just says A plus 0 is A. Do we need to do anything else? All right. I will see y'all next week.
Is our final in person or online?
In week 9, we have nothing new to study,
Okay,
but we still have class.
okay.
So I'm going to work the final up here, and you can work it out there, like as if we were doing homework. Or you can take it on your own. I don't care.
Okay. That sounds great. That sounds great. Well, we'll work.
okay. Yeah, we did. Because we were working on it, so this one. Okay, okay, because the first one I did it and I did not put it, oh my god. You do.
My sister like panicked. I'm like, girl, ooh, you want to see a cool X-ray of a I work at Kingston, my friend. I sent it to my friends and she was like, you should have told me to see it. And I'm like, oh, which is he fell off his bed, whatever. We don't know. But he had to get surgery. He had a broken femur. Like, look how broken that is.
Wow. My daughter, she broke her wrist and she was playing, she slipped at school. So when I picked, they called me, but her arm was exposed, got to the hospital. So when he started taking the x-rays, when he was moving, she was crying. I said, she broke.
Okay, so
He
for
said, "Come
this
here, Mom,
part,
show this
like,
now."
did we have to do research for this part?
The worst part was when she had to.
Okay, because I found it, okay, because I did obviously
Almost
more,
died.
I did this whole thing like wrong, because I thought I had like draw
My
out
husband
each
was a
triangle.
champ, he was holding her.
Well, there's an
and
infinite
his
number of
bones
them, you
so heavy.
Well, I know, that's what I said, yeah, but I did all of this and it was wrong, so I squared it except square rooting it. So, so I did like this part for my math, and I like found this article, and it used like dosage calculation. Is that like totally not what I was supposed to do?
Is it a movie or popular
It's like
whatever?
a medical journal. I thought that was like a movie.
Well, it said to find a movie or an article or a news event or something like that.
Newspapers, scientific research papers.
It said scientific research paper? Okay, cool.
Yeah.
As long as it is a scientific research paper and not,
This is where I found it.
No, I was gonna say we're hiring, but,
And it talks about like oxycontin.
show me what it is.
Yes. Okay, look. Okay, hold on.
but no one.
Not this one. It was this one.
Like I worked on.
Yeah, okay, yeah, it was talking about like healthcare, and it was talking about like the oxycontin and like that whole like opioid
You
crisis.
need certs, you can get your EMT.
And then it was Colgate.
It's not,
I know I heard it, but it's like.
but it's.
I'm trying to do that.
Why don't you, how much invested do you have in this?
They do get paid, they get paid.
Well, I had the whole thing wrong. Well, not the whole thing wrong, but at least I have the math part right. So I
You're
have
gonna
to
take statistics here?
So
No,
you let
already
me know, they give you a
That's a shame.
bonus, and you can split it.
So-
Bonus, you might get it.
Okay. Yeah, see, like I did like this part of the math, because I thought like with the discussion board, I drew out like each isosceles triangle, and I came up with like numbers, but I squared it. That's not what I was supposed to be doing, because it's the whole, like that part's wrong. I didn't realize it was that simple.
Nursing stuff, you can go.
But I wrote like this part for like the math, about like doing like the research,
But right now,
and it's like dosage calculations.
I was trying to get this too.
Why don't you elaborate more on this part? That's interesting to me.
The anesthesia, okay, yeah, and I found that from the article.
Dosage calculations, while you guys will be doing them in your career,
That's not
are
related.
boring.
Yeah, it is.
They're trivial,
in a year, you
virtually.
do IVs and all that too.
So,
No, we don't.
so, I mean, It really doesn't have to be very much at all. A lot of people will say stuff like, I mean, pick any movie that talks about math, Hidden Figures, Good Will Hunting, Mean Girls, you name it. And then they discuss the problem that was talked about. But then you have to say if they were right. Well, a scientific research article is likely to be right.
Yeah.
However, that came from the DataPine blog, which is not reputable.
Oh.
I'm sure it's probably right, but it's not a scientific research article. It's some person.
Right. And I did argue, so like the one part about like the Oxycontin one, it was actually wrong, and I argued why it was wrong.
Okay.
But it was like this part. It was about, they had like a graph. It was, let me see, it was like right here. It was like this graph, and then I argued why it was wrong because they were using Colgate, or in other words Oxycontin, as like a medication that it was like, oh, it's not addictive, like people can't get addicted on it, but it'll help, like, you know, with their symptoms. But it's like they were doing that to prove that the drug was not addictive because it stayed on the patient's blood over time, avoiding symptoms of withdrawal. But I said it's incorrect because the graphs are making it look like Oxycontin had very little effect. Meanwhile, it did, because it turned into the whole opioid crisis and it killed people. So that's why I argued it was wrong. Is that like not good, or?
It's not true that it had very little effect. It's one of the strongest.
That's why I said it. That's why I said it was incorrect, because it had a lot, like it had a big effect.
So you said that's not true because making it look like, oh, okay, making it look. So how about it made it look like it was, I mean, so Purdue tried to claim, hey, what are these graphs?
It's this.
What is the vertical?
I know, that's what I'm trying to read. All I know is that like their numbers, it is not like, it doesn't match up.
They are the same graph. first of
Yeah,
all,
yeah.
Because this is logarithmic and this is linear.
Mm-hmm. This
Okay.
one says hours from dosing, and then I think this
And
one.
what is the label on the vertical?
That's what I'm trying to find.
Oxycontin concentration.
Yeah.
Okay. And so, can't open that picture?
No, that's what I wish.
So,
Like, I mean, is that a good example if I was to use that one instead of the other one?
I would want you to say something about the reason is because of the half-life of OxyContin being longer than previously prescribed opiates. With that long half-life, the blood serum concentration is staying sufficiently high to avoid withdrawal symptoms within the period of time they're measuring. However, with, like, let's say, pharmaceutically administered fentanyl has a very short half-life.
Mm-hmm. Because, like, if you take one, like, you're gonna die from the fentanyl.
You know, they administer it in the hospital.
No, I'm saying, like the pills, like, nowadays.
Well,
Well, yeah,
nowadays,
if it's
people
monitored.
overdose on it.
Right, yeah, in the hospital, yeah, if you're monitored on it.
So, fentanyl has a very short half-life.
Mm-hmm.
Many other opiates have a much longer half-life.
Which would be like Oxycontin.
That is why they choose to administer fentanyl, like in a surgery or whatever,
Mm-hmm.
because it'll wear off quick.
Yeah.
And if Purdue leveraged the long half-life to deceive regulators about the addictive properties, then that was definitely a place where they were wrong.
Okay. So you're saying, like, when I said, like, the graphs were incorrect in making it look like Oxycontin had very little effect, this caused many deaths and ruined many families? That's just, like, too simple.
That's too simple. It didn't have very little effect. It had a pronounced effect.
So, okay, so if I was to elaborate on this.
I wouldn't say very little effect. I would change that to say
the graphs were incorrect and making it look like Oxycontin.
did not have withdrawal symptoms comparable to other opiates due to OxyContin's longer half-life than
Hold on.
more traditionally used
That's too
opiates.
fast. Okay, so wait. Okay, so making it look like Oxycontin did not have any withdrawal symptoms